Honored to be here, and thanks to Robert and all the group for setting up such a great event and really enjoying the atmosphere, and I'm learning a lot in this context, so thanks a lot. I will talk about bounds for multi-horizon stochastic optimization with application to energy systems, and these works that I'm going to present are based on a collaboration with great colleagues and co-authors, Professor Elisabetta Levi, Guzin Bayraksa, Laureano Scudero, Giovanni Micheli that is here, and he will talk about after my talk, Asger Tomasgar and Varaga Praya. So thanks to my collaborators and co-authors. So why optimization under uncertainty in energy systems? Many real-world decision problems in energy systems are, of course, affected by uncertainty, which means that there are sources of uncertainty that should be considered in the time that we make our decision. Think, for example, to renewable energy, solar plants, and so the energy produced by solar plants, or wind power plants, or reservoir inflows. At the time that we need to make our decision, we don't have a priori the full information about the realization of such a kind of random event. Secondly, in energy systems, we need typically to make a sequence of decisions over time, and in between such a pairs of decisions that we take over time, some random event can occur, such as the one that I've just mentioned. And of course, if we don't take them into account, our optimization solution can be not so reliable. Different are the modeling frameworks which allow us to incorporate the uncertainty in an optimization model. Stochastic programming is the one which is based on the assumption that we know the probability distribution of our random event. So this means that we need to have long historical data from which we can construct our empirical probability distribution, and more conservative approach are given by robust optimization, where we don't have any information about the probability distribution. We just assume that our uncertainty is in a certain support, and which is constructed in such a way to make the problem computationally tractable. More recently, another very popular modeling framework is given by distribution and robust optimization, which is in between stochastic optimization and robust optimization, where we assume to have a family of probability distribution, which are defined in a so-called ambiguity set, and we want to optimize, again, the worst possible probability distribution among the ones. Of course, this kind of modeling approaches are very challenging from a computational perspective, and among them, multi-horizon stochastic optimization is very suitable to model decision-making problems, especially for energy systems. So why multi-horizon stochastic optimization? Because in energy systems, we needed to consider not only the uncertainty, but uncertainty at different time scales. So at a strategic scale, which typically longs very long time periods, like years. And then after we have made this kind of decision at a strategic scale, we needed to take other decision at a lower time scale, like hour, which are related to so-called operational decisions. Example in energy systems about strategic and operational uncertainty are investment cost, carbon price, fuel price development, while at the operational level, for example, the load levels or the quantity of energy that we can get from wind for solar plants, etc. So incorporating these two types of uncertainty in our optimization model makes the problem particularly challenging, and the typical representation that we use in stochastic programming to represent it is the so-called multi-horizon scenario tree, where you have a big scenario tree, the one in red, representing the strategic uncertainty, and then nested inside each node of this strategic scenario tree, we have other operational scenario tree that are here represented in blue. So you see that the blue represent the operational uncertainty, while the red one, the strategic one. Describing in a suitable way the uncertainty at the both scale, strategic and operational, makes the problem particularly challenging from a computational perspective. And so this means that by increasing the number of stages and increasing the number of scenarios at strategic and operational, our computer can easily goes out of memory. So this means that approximation techniques are particularly important for such a kind of difficult decision problems. So I will try in this talk to try to answer to the following question. First of all, how we can provide approximation for this kind of problems based on expectation-based solutions, so by neglecting the uncertainty at strategic, operational, or both together. Then we will try to obtain other type of approximation by relaxing the so-called non-anticipativity constraints, which means that we assume to have the full information about strategic or operational or both at the beginning. And then we will try to propose other better bounds based on the concept of scenario grouping. So we still consider scenario trees, but of smaller dimension than the original one. And then we needed to combine them together in order to provide a mathematical guarantee lower bound to the original multi-horizon stochastic optimization problem. And finally, of course, how to provide a reliable solution, how to provide a feasible solution to our multi-horizon optimization problems, which can give us some implementable solution and mathematically an upper bound to the original multi-horizon stochastic optimization problems. I will show the numerical results of these different types of approaches on two problems, on a generation and transmission and expansion planning, and on a domestic renewable energy system design. So in terms of literature, multi-horizon stochastic optimization is quite a new topic in stochastic programming because the first papers are of 2012 and 2014 from the Norwegian group in NTNU. Mikael Kaut is in SINTEF, where they proposed the first model on multi-horizon stochastic optimization. After it, several approaches have been proposed in terms of methodologies able to cope with such a difficult problems, and the methodologies are mainly based on decomposition methods like Bender's, Lagrangian decomposition, time block decomposition schemes. In terms of application, we can see that most of the applications are in the context of energy, capacity expansion, multi-fuel energy markets, pump hydropower plants, etc. So, to the best of our knowledge, no contribution was available in the literature concerning bounds and approximation for such a kind of decision-making problems. And so, this presentation is in this context. So, we try not to make like decomposition schemes, even if we are working on it to integrate what I'm going to present now with decomposition, but we try just to consider a simplification of the original model and provide the bounds to multi-horizon stochastic optimization. So mathematically, we can then formulate our multi-horizon stochastic optimization through this difficult model, where you see that we have two types of decision. The red one are the strategic one, so this means are the decision that we needed to take on the nodes, and then on these red nodes, so in this red scenario tree, and then we have other operational decision denoted here with the letter Y, which are the one inside these subtrees. So the objective is to minimize the total cost, taking into account the strategic and the operational cost. And of course, since we are in the setting of stochastic programming, we assume to know what is the probability distribution of each node n inside the scenario tree, both at strategic and operational level. Then we have some constraints. The first two are just the constraints for the strategic scenario tree. These are just the constraints deterministic at the root node, then some linking constraints, and then we have other constraints which link the strategic and the operational subtree, and finally some constraints which are defining the dynamics of the operational level, and of course the decision variable of our problem. So starting from this formulation, then we try to provide some bounds via expectation-based approach. So one possibility is just to forget about the uncertainty at the operational level and simplify the problem according to this scheme. So we just substitute each of the scenario tree at the operational level with the expectation. And so we solve this simplified model, which we call multi-horizon operative expected value problem, which by construction is, of course, a lower bound to the original one. We don't know if it is good or not. We will see it later in the numerical experiments. Of course, another strategy is the opposite. So we consider the uncertainty at the operational level, but we just make the expectation at the strategic level. And this is another approach that we call multi-horizon strategic expected value problem. Also, this one provides a lower bound to the original one. And of course, a much more simplified approach is the one in which we forget about the uncertainty at the strategic and the operational level, and we just consider the expected value problem. And of course, this is the worst lower bound among the one presented. We will see later how they are related and how they perform compared to the other approaches. So they are like the state of the art, the basic approaches that we can do very easily to cope with these problems. Then another possible approach is, on the other hand, to keep the uncertainty, but assume that we have information about it at the beginning. So in other words, we would like to relax the so-called non-anticipativity constraints, which are a typical word, not so nice, but difficult to pronunciate in stochastic programming, which means that we need to relax the information about, we have more information about our uncertainty at the beginning. So one possibility is to define the so-called multi-horizon strategic wait-and-see approach, where what we do is to relax the non-anticipativity constraints only at the strategic level, which means that instead of solving the full multi-horizon stochastic program, we now solve a sequence of sub-problems, which are smaller, and where you have only one path at the strategic level, but still you have the whole information at the operational level. So you solve these 4 problems in an independent way, and then you need to combine them according to the probability distribution, and this provides a lower bound. This is another notation compared to the one presented before. This is a so-called scenario notation. We don't, because we have enforced explicitly these non-anticipativity constraints only at the operational level, but not anymore at the strategic one. Then another approach is, of course, to relax the non-anticipativity both at the strategic and the operational, and so this defines the so-called multi-horizon wait-and-see, where you see we don't have anymore any non-anticipativity constraints. So we can establish some relation among the different approaches. We have that they both the multi-horizon wait-and-see, so this one and the one presented before, are lower bound to the original multi-horizon stochastic program, and of course the first one was better than the second one because we still retain some non-anticipativity constraints. In particular, if we have that the coefficients in the objective function and the recurse matrix are fixed, so this means that the only uncertainty that we have is on the right-hand side terms, for example, in the demand, in the capacity, etc., then we can further establish this relation, which says that the multi-horizon expected value is a lower bound weaker than the multi-horizon wait-and-see, weaker in the sense that is far away from our multi-horizon stochastic program, and between the two expected value approaches, the multi-horizon expected value is lower than the multi-horizon operative expected value. So these kind of solution approaches are available in this paper that was the seminal one introducing bounds for multi-horizon stochastic programs. Then we thought to extend this idea of relaxing the non-anticipativity constraints with this approach that we call a multi-horizon cluster program with break stage H, which means that we decide a certain stage where we relax the non-anticipativity constraints. So we don't assume to have the whole information up to the end, but we assume that we split here the non-anticipativity constraint, but we keep the non-anticipativity constraints in the following stages. So by splitting just here, this means that instead of solving a 4 sequence of problems like in the wait and see, we just now needed to solve 2 problems. The first one on the left, and the first one, this one, and the second one on the right. And of course, then we can define to split these non-anticipativity constraints, for example, in later stages and so on. And so this can provide better lower bound with respect to the multi-horizon wait and see. Then, third question, how to bound a multi-horizon stochastic program using the concept of scenario grouping. So this is like a much more general framework, which has some connection with the non-anticipativity constraints, but allow to incorporate more possibilities. So the idea behind this approach is very simple. We assume to have already a finite number of scenarios, both at the strategic and the operational level. And we want just to split each of the scenario trees into some subgroups that we call here subproblems, which are independent, so problem 1, 2, up to a last one. And then we needed to find a way to combine their objective function value in order to provide a lower bound to the original one. Okay? So, in other words, what is the advantage of this approach is that instead of having a large problem, we now need to solve a smaller problem. Of course, the drawback is that we have more problems to be solved, but since they are smaller, they can easily parallelized. This idea actually is quite old in stochastic programming, was first of all introduced for 2-stage stochastic program by Burge, is also available in the book Burge-Louveau, Introduction to Stochastic Programming, and then we extend and modify and generalize in multi-stage and here multi-horizon stochastic optimization. So, putting a little bit of notation, this means that we are constructing a so-called refinement chain of lower bounds. So, in other words, I denote by capital Xi and capital Pi, respectively, the support and the probability distribution of the strategic level, while at the operational level, for each node, I have again another support and another probability distribution. So in other words, this representation represents my scenario tree at the strategic level, while at each strategic node n, we need to have another nested scenario tree at the operational level. So mathematically, this means that we split this capital Xi into some subgroups, capital Xi1, 2, etc., such that this kind of collection is a partition of the original problem, and we can partition into subgroups that are smaller and smaller up to arrive to the so-called wait-and-see approach. So in other words, here, if we start from the beginning, from the last level of this refinement chain, we just relax all the non-anticipativity constraints and we solve many deterministic problems in an independent way, while if we go one level up, we consider pairs of subproblems, so subgroups made just by 2 scenarios, and so on, up to go to the corresponding full description of the uncertainty. And then we associate to each of these supports a corresponding probability measures. In order to have a guarantee that this kind of combination provides lower bounds, we need to require some properties. So the first one is that at each level L of this refinement chain, the support is given by the union of the groups of the previous level, L-1 in the refinement chain, and this group can have some fixed scenario which are shared among all of them, or they can also be disjoint. The important property that we needed to satisfy in order to have a guarantee to have lower bounds is this one. So the original probability distribution can be rewritten as a convex combination of the probability distribution defined on each of these subgroups. It's convex, you see here, and each probability distribution can be written as a combination of the previous one level, so the level L-1. So I don't enter inside the mathematical proof, but thanks to this construction and this property, we can then prove that what we obtain by combining these subgroups is a lower bound to the original multi-horizon stochastic optimization problem. So graphically, for example, here think to have this multi-horizon scenario tree, we can just consider 2 subgroups at the strategic level, so the one on the left part and the other one on the right part. So we solve the 2 subproblems, and we define the probabilities such that they define the previous property, then we obtain a lower bound. We can do even the same exactly, but at the operational stage. So in other words, now we keep fix the uncertainty at the strategic level, and we just play around the probabilities at the operational level. Again, we need to satisfy this sequence of properties on the supports and on the probability. So again, the probability needs to be rewritten as a convex combination of the probability at each level gamma, and in between two consecutive levels, each probability for each group should be written as a convex combination of the previous level. So graphically, this means that if this is our original multi-horizon scenario 3, now we still keep fix the strategic uncertainty, and we play around the operational sub-3. For example, we solve this problem with just the left part of the operational sub-3, and then the second problem with just the right part of the operational sub-3. Again, these are smaller than the original one. And then we need to combine according to suitable weights. So what we did was to define two types of measure. One is called multi-horizon nodal group, and the second one multi-horizon expected group. They are based on the different way in which we weight the different types of subproblems. And then the main proposition is the following one. So we can establish a monotonically increasing or non-decreasing chain of inequality with respect to our multi-horizon stochastic program. So gamma represents the level at the operational level, while L represents the strategic level. So this means that if we go up at the last level of this refinement chain, both at strategic and operational, we actually reach the multi-horizon stochastic program, and then we can provide a monotonic chain of lower bounds. So according to our computational power, the powerful of our engine that we have at our disposal, we can stop at some level of this refinement chain and say that we are close enough to the multi-horizon stochastic program. Graphically, we can see here two representations of these two types of monotonic refinement chain. In this one, we work on the strategic level, while in this one, we work at the operational level. So in other words, at the top, we have the multi-horizon scenario 3. Here we split into two strategic subgroups, and then each of these subgroups is split again in other two subgroups. And so this means that if you solve these four subproblems and you merge them, then you obtain a lower bound that is weaker than the one that you obtain by merging the objective function of these two with respect to the original one. Secondly, here we have another chain where here we just consider deterministic values at the operational level. And then if you merge a pair of them, you obtain this type of scenario 3 and this type of scenario 3 for the second part. If we merge them, we obtain a lower bound to the original one that is better with respect to the last level of the refinement chain. Of course, I don't enter inside the technicalities. As I said, we had defined two different ways to combine these groups. The second one is called multi-horizon expected group. And the main difference is in how we define the weight of these groups. So these are given by the product of the probabilities of the scenario that are kept in that groups. This is a little bit technical. Why we have considered this second type of lower bounds? Because this also numerically provides a better lower bound compared to the one that I described before, but of course is more computationally challenging because it requires to solve many problems. For example, here for this simple scenario 3, this requires to solve 8 problems instead of 2 problems that we have required to solve for the nodal representation. So it's much more challenging from a computational perspective, but we have proven the theory behind also this kind of construction of lower bounds. I would like finally to present how we can provide some feasible solution to the multi-horizon stochastic optimization problem. So in other words, how to construct reliable upper bounds. Of course, the possible and easiest way is just to take a solution coming from the deterministic approach and inserting inside the multi-horizon stochastic program. So we are making like a so-called out-of-sample evaluation. For example, if we just consider the expected value problem, where we have a relax, where we have considered the expectation, what the strategic and the operational level, and we substitute the decision, respectively in the first stage, second stage, etc., we obtain a monotonic chain of upper bounds. More are the decisions that you fix from the deterministic, weaker is the upper bound. Okay, we are far away from the optimal one. You will see also numerically that this kind of approach, even if it's correct, is quite weak from a computational perspective because it can provide very loose upper bounds. So for this reason, we propose a second approach, which is like a rolling horizon approach, which is described by this algorithm, but of course now I don't enter inside the technicalities. I will just describe this, how it works, this kind of rolling horizon algorithm through a graphical representation. So in other words, in this algorithm, we decide a priori the number of stages and that we wanted to relax or not. So the one that we wanted to keep inside our subtree or the one that we think should not be considered. And the probability that we wanted to assign to each non-relax node. For example, in this case, suppose that we consider as equal to 2 the number of not relaxed stage and 1 the number of relaxed stage, and the probability to select a node in a certain stage equal to 1/2, then this scenario tree can be solved in this way. So we solve this two-stage, from a strategic perspective, problem, where you see that we put 1 divided by 2 the probability for the nodes that are not considered inside this scenario tree. We store the solution from the first stage, and then we go one step further, but respectively to the classical rolling horizon approach, here we don't consider the whole multi-horizon subtrees that can be constructed starting from the stage number 2, but we construct by considering only a portion of the nodes that can be considered, again according to a predefined probability of that kind of node. So going up one stage, now we solve and we store this second stage solution, and then we go one stage further up to arrive to, of course, the last stage. So this is the heuristic approach that we propose, and this is appeared in this paper that is actually under review in IEE-TUGraz. And I would like now to show some numerical results on comparing these different types of lower and upper bounds to see the advantage of such a kind of construction. So the 2 case studies that I'm going to present are the following. First of all, we consider a generation and transmission expansion planning, where we needed to decide how to invest in generation, in transmission and storage facility in order to supply at minimum cost the electricity demand and at the same time achieving some decarbonization targets. The decision at the strategic level are on the capacity for generation, transmission and storage that we needed to install for the long term, while at the operational level we needed to how to operate the power system in order to supply the demand over the day, taking into account some representative days. The uncertainty that we had to consider are at strategic level the investment cost and the fuel price, while at the operational level the uncertainty related to the production of solar, wind energy and natural inflows. The model was quite complex to consider all this kind of uncertainty together. The objective function considers a minimization of the total cost of the system, where we consider the strategic cost related to investment, while the second part is related to the operational cost. The objective function is related to the cost of independent system operator, or can be also an authority or a regulator. And then we needed to consider some constraints related to investment, operational constraints, and policy constraints. In terms of investment constraints, these are decided at the strategic level. So we needed to define the total capacity as the sum of existing and the new capacity that we want to install. And then we needed to decide some upper bounds to the installed capacity at the horizon. At the operational level, we needed to impose some constraints which satisfy the load in a representative day, upper bounds on the operational decision variables, and energy balance and the minimum energy levels for the storage facilities. So finally, we have also some policy constraints which are related to the maximum CO2 emission, and also we needed to allocate a quantity on non-programmable renewable power plants. So this is the whole model. And of course, for this was implemented using data for the Italian power system. The Italian power system is divided in 4 zones: North, South, Sicily, and Sardinia. They are connected by these 4 transmitting lines. We consider 4 technologies and 3 storage technologies, and as a target years, so at the strategic level, we consider the current year, 2025, where we need to take the decision, in 5 years and in 15 years, so 2030 and 2040. Here are just the dimension of the small instance and large instance case. So this means that we consider the strategic level in the small instance only 2 stages. These are the number of nodes, while the operational scenario per strategic stage are 64. So the difference with respect to the large instance is in the description of the strategic uncertainty, while we keep the same number of operational scenario at the operational one. We can see that we can obtain the optimal solution for the small instance case, but for the large instance, unfortunately, we were not able to assess to the optimal value. So let's start with the solution obtained via the much simpler approaches, so the one based on expectation, so the one that I presented at the beginning of the talk, and the one based on relaxing the non-anticipativity constraints. We can see in this column the results for small instance and here for the large instance. In the small instance, we can access to this percentage gap because we were able to obtain the optimal solution, while in the large instance, this percentage gap is computed with respect to the best upper bound obtained through the rolling horizon procedure just described. So we can see that the expectation-based approaches are very weak, of course, as expected. Of course, the weakest one is the one in which you just forget about the uncertainty. And if we consider the uncertainty at the strategic level, but not of operational, we get a percentage gap of -17. Similar is the trend also for the larger instance, even if the percentage gap are smaller. In terms of upper bounds, we see the best upper bound obtained, respectively, by fixing solution from the deterministic approach and the rolling horizon. Of course, we see that the lowest value is obtained by the rolling horizon approach, which outperforms the one based on expectation. However, can we do better? Better results are, on the other hand, obtained by considering this grouping idea. These are the results in the small instance case, where you can see for different level of the refinement chain at the operational here and the strategic here, the percentage gap obtained. So, for example, this table refers to the multi-horizon expected group, while the second one on the nodal group, so the 2 approaches that we have proposed. And if we want to solve a full model, of course, the percentage gap is 0% and is displayed in this corner. So going down in this refinement chain, so this means that we are splitting the operational uncertainty, but we are keeping the whole strategic uncertainty. We can see that going down, as expected, brings to worst lower bounds. And we see that by considering the expectation group approach, at a certain point, we are not able to solve the problem because it requires too many subgroups to be solved. On the other hand, using the nodal construction, so the one based on the convex combination of probability distribution, we can see that we can get access to the whole chain of lower bounds, both strategic and the operational, and we can see that, in this case, it plays an important role, the operational uncertainty, even if it was not expected, instead of operational, the strategic one. In the case of large instance, here are the results obtained for considering these Jones subgroups. In this case, we were not able to solve the full multi-horizon problem. So as you see here, we cannot get access to the optimal objective function value. And so we can see that by going down in this refinement chain of lower bounds, we pass from minus 0.34 to minus 5.35, while working at the level of a strategic chain, we can see that the worst lower bound, in the case we keep the whole groups at the operational level, is minus 6.71. So of course, according to these results, the best lower bound is obtained just by splitting into the strategic subtrees and keeping the operational subtree and keeping the whole strategic chain. If you want to go further, so by splitting both operational and strategic chain, you can see that in this case the worst lower bound that you obtain is minus 12.60, much better than the one presented before through the expectation-based approaches. And here are just reported the CPU times. And here is graphically their lower bounds behavior and the CPU times. In this case, since we were not able to solve the whole model, these percentage gap are computed with respect to the best upper bound obtained, which was obtained through the rolling horizon procedure. Okay, so 286.93. The second case study that I would like to present, again related to energy systems, is a domestic renewable energy system design, where we wanted to define the planning on investment on PV panels and batteries in order to supply energies to residential building complex. This is a work done in collaboration with Laureano Scudero that brought the original problem to be considered. So the decision variables are at strategic level, the capacity of a photovoltaic panel and the batteries in the long term, while at the operational level we needed to decide the generation, storage and electricity exchange with the grid to supply the demand in every hour of a representative day. The uncertainties that we had to consider in this case are at the strategic level, the investment and maintenance cost, while the operational level, the solar radiation, electricity price, and electricity demand. The experimental setup was based on data provided by southern Germany. So this location was located, this building was located in Germany. We use 3 types of photovoltaic panels, 2 types of batteries, and we have considered sources of data coming from these data sets. Also here we consider different types of dimension for our setups, so small, medium and large case. And here again are described the number of strategic nodes, strategic stages, strategic scenario and operational scenario per node in the small, medium and large case. And the dimension of the optimization problem obtained is here reported. In this case, we were able to solve without making a splitting procedure the small case and the medium case, but we were not able to solve the largest case. So here we tested some of the approaches that I presented before. We didn't test the grouping approach, but we tested the expectation-based approach and the one in which we relax the non-anticipativity constraints at a certain stage. So the one in which we cut the non-anticipativity constraints, for example, in stage 2, 3, 4, and 5. They all provide lower bounds, and so we can see that the best lower bound obtained is the one by splitting the non-anticipativity constraint at the strategic level at stage number 2. as expected. While in terms of upper bound, we see here the upper bounds obtained through the rolling horizon procedure, so the one in which we just go up in the scenario 3 and we fix the solution obtained in the first stage strategic node. Here we see for small, medium, and large instances for different parameters, so for different numbers of fixed and so relaxed and non-relaxed nodes and the probability to choose or not a node inside the subtrees. We can see that here the optimality gap are very good, and in particular also in the large case instance, the percentage gap was 0.69, and we are now currently working on the revision of this article, making comparison with other state-of-the-art approaches, and the percentage gap is better than the one available in the literature, based of course on this kind of application. So, in conclusion, in this talk, I have proposed a different type of bounds and approximation for multi-horizon stochastic optimization problems. The different types of bounds are based on operational expected solution from a strategic and operational case. And we have proposed bounds relaxing the non-anticipativity constraints, and on the idea of scenario 3 decomposition through group subproblems. The take-out message that I would like to give is that this kind of bounds are, even if, could be, you could think that it could be difficult to solve these different subproblems, but the good news is that they are general in the sense that they can be applied to linear problem, quadratic problem, integer problem, binary problems. So we don't ask any requirement in terms of the type of model. So we now work on splitting the uncertainty. Okay, so this is, they provide guarantee bounds, but they are applicable to a broader class of problems. The current research direction is to integrate this kind of bounds through the composition approach, like Bender's decomposition. And we have tested the fact that by adding cuts for each of the subgroups, instead of adding for each scenarios, like in the multi-cut or in the single-cut version of Bender's, can accelerate the convergence of the algorithm. And then another research direction is to provide bounds for distribution-robust multi-horizon problems, provide bounds for the decision-dependent case, and more recently we are also working on how to integrate neural network to solve multi-horizon stochastic optimization problems. So in other words, to provide some surrogate neural networks which describe the operational uncertainty and plug inside the strategic one. Here are some references. So the expectation-based bounds are in this paper 2020, while the one based on relaxing non-anticipativity constraints and on grouping are reported in these two papers that are in preparation, and one is available in archive. So I hope to be in time. Thanks a lot for listening, and thanks again for the invitation.